voltage measured between 1 and 2 volts is called ground loop voltage. It occurs when electrical circuits share a common ground path but have different voltage potentials. In this case, the neutral wire from the branch circuit which feeds the outlet is connected to the neutral bus in the sub-panel. The sub-panel also serves three-phase equipment. When these three-phase loads draw unbalanced currents, it can cause the neutral wire to carry current, creating a voltage drop between the neutral and ground. Electronic devices can be sensitive to ground loop voltage. The electronic scanner may interpret this voltage as noise or interference, which can disrupt its operation. An isolation transformer can be a solution for ground loop voltage. It isolates the secondary circuit, in this case the scanner, from the primary circuit, which is the branch circuit from the sub-panel. An isolation transformer has two separate windings. The primary winding is connected to the branch circuit, and the secondary winding is connected to the scanner. The magnetic coupling between the two windings transfers power from the primary to the secondary, but it also blocks any ground loop voltage. To install an isolation transformer, connect the primary winding to the branch circuit and the secondary winding to the scanner. Follow the manufacturer's instructions carefully. Firstly, isolation transformers eliminate ground loop voltage. Secondly, isolation transformers improve electronic device performance. Thirdly, isolation transformers provide additional isolation between the scanner and the power source. Ground loop voltage is a common problem in electrical systems, especially when sensitive electronic equipment is involved. It arises from the fact that the ground is not always at a uniform potential throughout the system. Ideally, the ground should be a perfect conductor with zero resistance, ensuring that all points on the ground are at the same potential. However, in reality, ground wires have some resistance, and when current flows through these wires, it creates a voltage drop. This voltage drop is what we refer to as ground loop voltage. The primary cause of ground loop voltage is unbalanced current flow in the neutral conductor. In a balanced three-phase system, the currents in the three phases are equal in magnitude and 120 degrees apart in phase. This results in the neutral conductor carrying very little current. However, in most real-world scenarios, the loads on the three phases are not perfectly balanced. This imbalance causes current to flow in the neutral conductor. Since the neutral conductor is connected to the ground at the service entrance, any voltage drop along the neutral conductor will appear as a voltage difference between the neutral and ground at various points in the system. This voltage difference can create problems for sensitive electronic equipment. Electronic devices are designed to operate with a clean and stable ground reference. When ground loop voltage is present, the device may interpret this voltage as noise or interference. This can lead to various problems such as data errors, malfunction, and even damage to the equipment. The magnitude of ground loop voltage depends on several factors, including the amount of unbalanced current, the resistance of the neutral and ground conductors, and the distance between the equipment and the service entrance. In some cases, the ground loop voltage may be only a few millivolts, while in other cases it can be several volts. There are several methods for mitigating ground loop voltage. One common method is to use an isolation transformer. An isolation transformer is a transformer that provides electrical isolation between the primary and secondary windings. This means that there is no direct electrical connection between the input and output circuits. The power is transferred from the primary to the secondary through magnetic coupling. Isolation transformers are effective at reducing ground loop voltage because they break the ground loop. The secondary winding of the isolation transformer provides a clean and stable ground reference for the connected equipment. Any ground loop voltage on the primary side of the transformer will not be transferred to the secondary side. Another method for mitigating ground loop voltage is to use a dedicated ground wire. A dedicated ground wire is a separate ground wire that is run directly from the equipment to the service entrance. This provides a low impedance path for ground currents and reduces the voltage drop along the ground wire. In addition to these methods, it is also important to ensure that the electrical system is properly grounded and that all connections are tight and clean. Loose or corroded connections can increase the resistance of the ground path and exacerbate ground loop voltage problems. When troubleshooting ground loop voltage problems, it is important to use the multimeter to measure the voltage between the neutral and ground at various points in the system. This will help to identify the source of the ground loop voltage. It is also important to check the grounding system to ensure that it is properly installed and that all connections are tight and clean. In some cases, it may be necessary to consult with a qualified electrician to diagnose and resolve ground loop voltage problems. Ground loops can also occur in audio and video systems. These ground loops can cause hum and noise in the audio signal or distortion in the video signal. The causes of ground loops in audio and video systems are similar to those in electrical systems. They are typically caused by multiple ground paths between different pieces of equipment. For example, if two pieces of equipment are connected to the same power outlet and also connected to each other through a shielded cable, this can create a ground loop. The shield of the cable provides a ground path between the two pieces of equipment. To prevent ground loops in audio and video systems, it is important to use equipment with isolated grounds. This means that the ground connections of the equipment are isolated from the chassis. It is also important to use shielded cables and to avoid creating multiple ground paths between different pieces of equipment. In some cases, it may be necessary to use a ground loop isolator. A ground loop isolator is a device that breaks the ground loop without interrupting the signal. Ground loop isolators typically use transformers or optocouplers to provide electrical isolation. The key to understanding ground loop voltage lies in recognizing that the ground in an electrical system isn't a perfect 0-volt reference everywhere. It's a network of conductors that, while intended to be at the same potential, inevitably have some resistance. This resistance, combined with current flow, leads to voltage differences. Firstly, consider the neutral conductor. In a single-phase 120-volt circuit, the neutral is intended to carry the return current back to the source. However, when that neutral is also connected to the ground, as it typically is at the service entrance and often at sub-panels, it creates a parallel path for current to flow. If there is any current flowing in the neutral, and the neutral conductor has resistance, there will be a voltage drop along the neutral. This voltage drop means that the neutral at the outlet is at a slightly different potential than the ground at the sub-panel. That difference is the ground loop voltage. Secondly, think about the three-phase equipment connected to the same sub-panel. Three-phase systems are designed to be balanced, meaning that the currents in each of the three phases are equal and 120 degrees apart. In a perfectly balanced system, the neutral current would be zero. However, real-world loads are rarely perfectly balanced. This imbalance causes current to flow in the neutral conductor. The more unbalanced the load, the more current flows in the neutral, and the greater the voltage drop along the neutral conductor, leading to a higher ground loop voltage. Thirdly, the impedance of the ground conductor itself contributes. While the ground wire is designed to provide a low impedance path to ground, it's not 0 ohms. Any current flowing through the ground wire, such as fault current or even stray currents, will create a voltage drop. This voltage drop adds to the ground loop voltage. For sensitive electronic equipment like the scanner, this ground loop voltage can be problematic. These devices are designed to operate with a stable and clean ground reference. The 1 to 2 volts of ground loop voltage can be interpreted as noise or interference, disrupting the device's operation and potentially causing inaccurate readings or malfunctions. The isolation transformer offers a way to break this ground loop. By isolating the secondary circuit, which powers the scanner, from the primary circuit, which is connected to the sub-panel, it prevents the ground loop voltage from affecting the scanner. The transformer achieves this isolation through magnetic coupling. The primary winding is connected to the incoming power, and the secondary winding is connected to the scanner. There is no direct electrical connection between the two windings. Instead, the alternating current in the primary winding creates a magnetic field that induces a current in the secondary winding. This magnetic coupling allows power to be transferred from the primary to the secondary while blocking any voltage differences between the grounds of the two circuits. This is because the secondary winding floats relative to the primary winding's ground. The ground reference for the scanner is now established by the secondary winding of the isolation transformer, which is isolated from the noisy ground of the subpanel. When installing the isolation transformer, carefully follow the manufacturer's instructions. Ensure that the primary winding is properly connected to the branch circuit and that the secondary winding is correctly connected to the scanner. Pay close attention to the voltage and current ratings of the transformer to ensure that it is suitable for the application. In addition to using an isolation transformer, there are other steps that can be taken to minimize ground loop voltage. Firstly, ensure that the electrical system is properly grounded. This includes verifying that all ground connections are tight and clean and that the grounding conductors are of adequate size. Secondly, try to balance the loads and the three phases of the electrical system. This will minimize the current flowing in the neutral conductor and reduce the voltage drop along the neutral. Thirdly, use shielded cables for all connections to sensitive electronic equipment. The shield of the cable can help to block electromagnetic interference and reduce the impact of ground loop voltage. Ground loop voltage is a complex phenomenon that can be difficult to troubleshoot. However, by understanding the causes of ground loop voltage and taking appropriate steps to mitigate it, it is possible to ensure the reliable operation of sensitive electronic equipment. The problem arises because the neutral and ground conductors, while connected at the service entrance, are not perfect conductors with zero impedance. This means that when current flows through these conductors, voltage drops occur, creating potential differences between different points in the grounding system. In the described scenario, the sub-panel serves both single-phase 120 volts branch circuits and three-phase equipment. The three-phase equipment, especially if it's drawing unbalanced loads, can cause significant current to flow in the neutral conductor back to the main service entrance. This current flow through the neutral conductor's impedance creates a voltage drop. Since the neutral is connected to the ground of the sub-panel, this voltage drop is reflected as a potential difference between the neutral and the isolated ground of the single-phase outlet. Electronic scanners, like many sensitive electronic devices, are designed to operate with a clean and stable ground reference. The 1 to 2 volts of ground loop voltage can be interpreted by the scanner as noise or interference, disrupting its operation and potentially leading to inaccurate readings or malfunctions. The most effective solution is indeed to use an isolation transformer at the point of use near the scanner. An isolation transformer provides galvanic isolation between the primary and secondary windings, meaning there is no direct electrical connection between the input and output circuits. Instead, power is transferred through magnetic induction. This isolation breaks the ground loop, preventing the ground voltage from the primary side from affecting the secondary side, where the scanner is connected. The secondary winding of the isolation transformer establishes its unclean ground reference, effectively isolating the scanner from the noisy ground environment of the subpanel. When selecting an isolation transformer, it's important to choose one with the appropriate voltage and current ratings for the scanner. The transformer should be rated to handle the scanner's power consumption without overheating or causing voltage drops. Installation is relatively straightforward. The primary winding of the isolation transformer is connected to the existing 120 volts branch circuit outlet. The secondary winding is then connected to the scanner's power input. It's crucial to follow the manufacturer's instructions carefully and to ensure that all connections are secure and properly insulated. While an isolation transformer is the most effective solution, there are other measures that can help to mitigate ground loop voltage. Firstly, ensure that the grounding system is properly installed and maintained. All ground connections should be tight, clean, and free of corrosion. The size of the grounding conductors should be adequate for the expected fault currents. Secondly, try to balance the loads and the three-phase system as much as possible. This will minimize the current flowing in the neutral conductor and reduce the voltage drop. Thirdly, use shielded cables for all connections to the scanner and other sensitive electronic equipment. The shields can help to block electromagnetic interference and further reduce the impact of ground loop voltage. Fourthly, consider using a dedicated isolated ground conductor for the scanner. This involves running a separate ground wire from the scanner directly back to the main service entrance, bypassing the sub-panel's grounding system. This can provide a cleaner ground reference for the scanner, but it may not always be practical or necessary. By understanding the causes of ground loop voltage and implementing appropriate mitigation measures, such as using an isolation transformer, it's possible to ensure the reliable operation of sensitive electronic equipment in environments with noisy grounding systems. The presence of 1 to 2 volts between the neutral and the isolated ground on a branch circuit, especially one feeding sensitive electronic equipment like a scanner, is a strong indicator of a ground loop issue. Understanding the root cause and the mechanism by which it affects electronic devices is crucial for implementing an effective solution. Firstly, the ground in an electrical system is not a perfect zero potential reference. While it's designed to provide a low impedance path for fault currents and to equalize potential differences, it's still a network of conductors with some resistance. This resistance, however small, becomes significant when current flows through it, leading to voltage drops along the ground path. Secondly, the neutral conductor, which is intended to carry the return current from the load back to the source, is also connected to the ground at the service entrance and often at subpanels. This connection creates a parallel path for current to flow. In an ideal scenario, where the neutral and ground conductors have zero impedance, there would be no voltage difference between them. However, in reality, both conductors have some impedance, and when current flows through the neutral, a voltage drop occurs. This voltage drop is reflected as a potential difference between the neutral and the ground at various points in the circuit. Thirdly, the three-phase equipment connected to the same sub-panel plays a significant role. Three-phase systems are designed to be balanced, meaning that the currents in each of the three phases are equal and 120 degrees apart. In a perfectly balanced system, the neutral current would be zero. However, real-world loads are rarely perfectly balanced, leading to current flow in the neutral conductor. The magnitude of the neutral current depends on the degree of imbalance in the loads. The more unbalanced the load, the more current flows in the neutral, and the greater the voltage drop along the neutral conductor, resulting in a higher ground loop voltage. Fourthly, electronic scanners are highly sensitive to voltage fluctuations and noise on the ground reference. They are designed to operate with a clean and stable ground, and any voltage differences between the neutral and ground can be interpreted as interference or noise. This can disrupt the scanner's operation, leading to inaccurate readings, data errors, or even equipment malfunction. The 1 to 2 volts of ground loop voltage, while seemingly small, can be enough to cause problems for these sensitive devices. The isolation transformer is an excellent solution for mitigating ground loop voltage. It works by providing galvanic isolation between the primary and secondary windings, meaning there is no direct electrical connection between the input and output circuits. Power is transferred through magnetic induction, where the alternating current in the primary winding creates a magnetic field that induces a current in the secondary winding. This isolation breaks the ground loop, preventing the ground voltage from the primary side from affecting the secondary side, where the scanner is connected. The secondary winding of the isolation transformer establishes its own clean ground reference, effectively isolating the scanner from the noisy ground environment of the subpanel. When selecting an isolation transformer, it's crucial to choose one with the appropriate voltage and current ratings for the scanner. The transformer should be rated to handle the scanner's power consumption without overheating or causing voltage drops. Installation is relatively straightforward. The primary winding of the isolation transformer is connected to the existing 120 volts branch circuit outlet, and the secondary winding is connected to the scanner's power input. Follow the manufacturer's instructions carefully and ensure that all connections are secure and properly insulated. In addition to using an isolation transformer, consider these measures to minimize ground loop voltage. Firstly, ensure that the grounding system is properly installed and maintained. All ground connections should be tight, clean, and free of corrosion. The size of the grounding conductors should be adequate for the expected fault currents, as specified in the NEC table 250.122. Secondly, try to balance the loads on the three-phase system as much as possible. This will minimize the current flowing in the neutral conductor and reduce the voltage drop. Thirdly, use shielded cables for all connections to the scanner and other sensitive electronic equipment. The shield can help to block electromagnetic interference and further reduce the impact of ground loop voltage. Fourthly, consider using a dedicated isolated ground conductor for the scanner. This involves running a separate ground wire from the scanner directly back to the main service entrance, bypassing the sub-panel's grounding system. This can provide a cleaner ground reference for the scanner, but it may not always be practical or necessary, and must comply with NEC Section 250.130c. By understanding the causes of ground loop voltage and implementing appropriate mitigation measures, it's possible to ensure the reliable operation of sensitive electronic equipment in environments with noisy grounding systems. Remember that electrical work can be dangerous, so always consult with a qualified electrician if you are not comfortable performing the work yourself.